Good morning. My topic for discussion today is biomaterials. Moving on to introduction, over the last few years, new materials have come to light which mimics and repairs the defective restoration and most conservative approach and been called as biomaterials. Biomaterials has evolved into a new field which has revolutionized the face of dentistry. These biomaterials can be natural or synthetic, which helps in repairing the defects. Dental biomaterials have unfolded over the years from bio-inert materials to bioactive materials, which brings about cellular, morphological and molecular changes, which stimulates the tissue healing through regenerative therapy. The level of smartness of biomaterials can be classified as an inert, which is considered to be lowest, and then active, which releases some active components into the environment, and a responsive type, which is able to sense the environment and respond accordingly. And then you have the autonomous, where it will be able to adapt to the environment, and depending upon the stimulus, it is able to respond in a different way. So inert is mostly a biocompatible, it will not do any harm, that is no toxic reaction. Active biomaterials offer a one-way uncontrolled release of therapeutic components. Responsive can sense the specific signals found in the environment or biological process to then release the therapeutics. Autonomous biomaterials can sense a signal, release a specific payload and adapt their properties to the changing environmental condition to keep providing additional, advanced and alternative forms of therapeutics. So the goal of modifying the biomaterial surface is to create a specific chemical or physical environments that offer more favorable, often complex cellular and environmental responses. The modification of biomaterials can be done by modifying the electric charge, the porosity, by incorporating ion fillers, by increasing the wettability, by changing the biochemistry of the material and the topographic changes. The classification of smart materials include active smart materials and passive smart materials. The active smart materials are materials that shows alteration in the surrounding and react to it. They act passive smart materials, they observe the environmental changes and react to them without any outside influence. So we are going to discuss today about two biomaterials, of which we will be discussing now only with the MTA. So MTA was developed by Loma Linda University in 1990 by Torabinjit et al. This MTA it received acceptance by US Federal Drug Administration in 1998. First MTA which was designed was a grey MTA, and later there was a formation of white MTA. The composition of MTA includes tricalcium silicate, dicalcium silicate, tricalcium aluminate, tetracalcium aluminoferrite, calcium sulfate, bismuth oxide, calcium oxide, silicon oxide and aluminium oxide. The difference between grey and white MTA is that grey MTA has tetracalcium aluminoferrite and white MTA it is prepared by replacing this aluminoferrite, which is giving the color to the grey MTA, with magnesium oxide in order to prevent the tooth discoloration, because that was considered to be the major disadvantage with the grey MTA. Contains a large size particles, contains smaller particles with a narrower size distribution, and grey MTA has a longer setting time while white MTA has a shorter setting time. Grey MTA has a greater compressive strength, and while white MTA has a lesser compressive strength. There are various modifications in the mineral trioxide aggregate to make it a versatile dental material. It is considered to be one of the active and responsive biomaterial, because it is able to trigger the reparative dentin formation more when compared to calcium hydroxide. This tricalcium silicate and dicalcium silicate react with water to form calcium silicate hydrate and calcium hydroxide. The tricalcium aluminate reacts with water and in the presence of calcium sulfate produces ethylene initially. When the sulfate containing phases are depleted, a monosulfate phase is formed. So this is what is the setting reaction, where tricalcium silicate reacts with water to form calcium silicate hydrate and calcium hydroxide, while dicalcium silicate reacts with water to form calcium silicate hydrate and calcium hydroxide, while tricalcium aluminate and calcium sulfate reacts with water to form ettringite, a hydrous calcium aluminosulfate mineral. So MTA is a hydraulic type of cement, meaning that it is sets by reacting with water and is then stable in water. When mixed with water, it forms via an exothermic reaction. So these are the various different forms of MTA which can be classified into generations. The first generation, second generation and third generation and fourth generation. The first generation includes grey and white MTA. Second generation includes modifications of MTA. Example is MTA Angelus, and third generation is Endo-CPM. That is the Portland modified iRoot SP, also known as Endosequence BC and Smart Pace Bio. Then MTA Optera Tech Biosealer Endo, which comes under third generation. And then we have the which includes Biodentin, Ortho MTA, MTA Plus and Bioaggregate. And fourth generation MTA includes hybrid cements like calcium phosphate and calcium silicate bismuth cement. MTA with 4 meta and light pure cement including Terracal comes under fourth generation of active biomaterials. So what are the advantages of this MTA as a dental material? It improves the improvised setting time is there. Why we have to modify the original MTA to a newer version is that it improvises the setting time. There is no longer a longer setting time where we have to wait for long hours. Now fast setting MTA available, enhance compressive strength and micro hardness, overcome fracture, overcome root perforation, increase the radio opacity and reduce the tooth discoloration, enhanced antibacterial activity, regenerative ability is greatly enhanced, enhancing the biocompatibility in drug delivery. The compressive strength of MTA is 24 hours of mixing was about 40 megapascals and increases 67 megapascals after 21 days. The mean radio opacity of MTA is 7.17 millimeters of equivalent thickness of aluminium. The solubility includes the MTA shows no signs of solubility. MTA seals very superiorly and no gaps were found in any of the experimental specimen. MTA has also proved itself to be superior in bacterial leakage. Reaction with other dental materials, MTA does not react with any of the restorative materials, so it seems to be compatible with various cements. And biocompatibility of MTA is that it is able to induce the reparative dentin formation. It is also able to have a tissue regenerative property which is capable of activating the cementoblast and produces the cementum when placed on the root perforation repairs, and it is also able to induce the calcium hydroxide, like calcium hydroxide induces the dentin bridge formation. Okay, the formation of dentin bridge by MTA seems to be very good comparatively to the dentin bridge induced by calcium hydroxide. So what are the characteristics of MTA is that the setting type of MTA is about 2 hours, but now fast setting of MTA is available which sets within 30 minutes. It is highly radio opaque, sets in the presence of moisture. The pH is initially 10 and followed after 3 hours it becomes 12, and then MTA has no solubility and it is highly biocompatible, having an antimicrobial property also, and it is non-resorbable, minimal leakage. The compressive strength when it develops over a period of 28 days and it increases to 133 megapascals. The main use of MTA is that it is used in the pulp capping procedures like direct or indirect pulp capping. It is used in pulpotomy procedures. It is used for furcation perforation repair. It is used in the repair of lateral perforation. It is used in the apexogenesis, apexification procedures and also root resorption.